Hi everybody. In this video I'll show you how to compute the axis-aligned bounding box of a transformed ellipse. This approach is fast and guarantees exact results for any linear transformation. We begin with a unit circle. Its bounding box is a square aligned with a coordinate axis. Now let's apply some transformations. Scaling stretches the circle into an ellipse. Rotation spins the figure around the origin, and shearing distorts it diagonally. In each case, the bounding box changes to fit, but it remains axis-aligned. That's the key constraint. To compute the bounding box, we need to find the tangency points between the bounding box and the transformed ellipse. A typical method in graphics is to represent the ellipse using Bézier segments and then estimate bounding limits through curve extremer. It works, but it's more complex than necessary. So in this video, I'll show you a much smarter and exact method. Let's define some things first. A transformed ellipse is the image of a unit circle under a linear transformation represented by matrix A. If your starting figure is an ellipse, you just need to multiply the ellipse's transformation matrix with the scale matrix of the unit circle to get matrix A. The bounding box is axis-aligned, its horizontal edges have slope 0, and its vertical edges have infinite slope. So, rather than working with the ellipse directly, we start with the unit circle and compute the tangency points there. Then we apply the transformation matrix to map those points onto the ellipse. Here's the detailed approach. First, we compute the original slopes m1 and m2. Then we find the tangency points on the unit circle. We apply matrix A to those points. And finally, compute the bounding box by taking the minimum and maximum of those transformed coordinates. Let's start with m1, where m1 prime is 0. Consider point P at 1 m1 along a line from the origin. To make the transformed line horizontal, the second coordinate of A times P must be 0. That gives A21 plus m1 times A22 equals 0. So m1 equals negative A21 over A22. Next, we find where this line intersects the unit circle. Using the intercept theorem, we get point Q. Then we rotate Q by 90 degrees to get T1 and by negative 90 degrees to get T2. In the special case where A22 equals 0, T1 is at negative 1, 0 and T2 is at 1, 0. Next, we compute M2 where M2 prime is infinite. This time, point P is at M21. We want the transformed line to be vertical, so the first coordinate of A times P must be 0. That gives M2 times A11 plus A12 equals 0. So M2 equals negative A12 over A11. Once again, we find Q on the unit circle using the intercept theorem and rotate it by 90 degrees to get T3 and by negative 90 degrees to get T4. In the special case where A11 equals 0, T3 is 0, negative 1 and T4 is 0, 1. Now we have all four tangency points. Apply matrix A to each point. And then Calculate the bounding box by taking the minimum and maximum x and y values across the transform points. That gives you the exact axis-aligned bounding box. That's it.